introduction in our group assignment, which is the title is Electron Microscope, Geology and Earth Science. So, electron microscopy is an imaging technique widely used in geology and earth science to investigate mineral, rock, and geological microstructures. Unlike conventional light microscopes, which are limited in resolving extremely small, instead of light producing much higher resolution and magnification. Therefore, nanoscale to atomic scale imaging become possible, allowing detailed observation of mineral morphology, pore network, crystal structure, and rock texture. As a result, electron microscopy has become an essential tool for understanding earth material, geological process, and the evolution of rock microstructure, according to MAETL 2024. Hi, it's me again. So next, I would like to talk about the significance of electron microscope in geology and earth science. So, rocks and earth material contain minerals and microstructure that preserve evidence of their geological history. Scanning electron microscope is microscope that helps reveal these features at micro to nanoscales. Hence, signals produced by beam sample interaction are detected to form scanning electron microscope image showing particle morphology, texture, shape, and surface features. Understanding this characteristic helps researchers identify mineral, interpret geological process, and explain why certain minerals exhibit unique properties and behaviors. Therefore, without the electron microscopy, many of these microscopic features would remain difficult to observe and study, according to OZAC 2025.
Now, let's get to know about types of electron microscope with me. So basically, there are two electron microscopes that are commonly used in the industries, which are scanning electron microscope and also the transmission electron microscope. Scanning electron microscope, or SEM, can be used to observe the crystalline structure, surface topography, and also the chemical composition of the top part of the specimen. Or in other words, basically, scanning electron microscope is used to examine, to analyze, or to observe only the surface part of the specimen, since the beam of light cannot penetrate through the specimen. Next, SEM has a magnification of 1 million times that can reach the nanometer scale, which allows an in-depth examination of the specimen. Other than that, SEM also has a large field of depth that help to maintain the focus of the specimen simultaneously. And the last one is SEM can provide all the information about the external surface of the specimen, since scanning electron microscope is used to examine or to observe only the surface of the specimen. So it can provide any types of information that we need just by using scanning electron microscope. Now let's move on to transmission electron microscope. Okay, so the electron beam of the transmission electron microscope, or TEM, which strikes the sample and transmit through its thin surface of the specimen to view the inner part of the specimen. Other than that, TEM has a magnification of 50 million times that can be able to analyze the internal surface of the specimen very clearly. Next, it also can provide detailed information about the morphology and also the chemical composition of a sample, either qualitatively or quantitatively. And the last part is, it can provide crucial information about the internal composition of the specimens. Like I said before, transmission electron microscope can analyze or observe the inner part of the specimen, so it can give any type of information that we want just by using the transmission electron microscope. Now, let's move to detector attachment in electron microscope. For scanning electron microscope, there is a lot of detector, and some of it is BSE, or backscattered electron imaging, and also EDS, which is energy dispersive spectrometry. The function of BSE in scanning electron microscope is to determine the compositional information by detecting the electron reflected from the sample surface due to interactions with the primary electron beams. Meanwhile, the function of EDS in scanning electron microscope is to identify and quantify the elemental composition of a sample by detecting the characteristic X-rays emitted when the specimen is irradiated by an electron beam. Now, let's move to transmission electron microscope. Bright field and annular bright field is one of the detector that presents in transmission electron microscope. Now let's focus on bright field first. Okay, so the function of bright field is to collect electron that's scattered forward at low angle to reveal bulk information or sum of information throughout the thickness of the sample. Meanwhile, for annular dark field, the function is to collect electrons that scattered forward at high angle to reveal the structure and atomic information throughout the entire thickness of the sample.
Hi, for this slide, I would like to talk about the electron backscatter diffraction technology. So let's go to the background. Firstly, electron backscatter diffraction is an microstructure characterization technique integrated with a scanning electron microscope. It is used to analyze crystallographic information such as crystal orientation, grain boundaries, phase distribution, and deformation behavior within materials. Furthermore, electron backscatter diffraction enables researchers to study the evolution of microstructures during deformation, providing information that cannot be obtained through conventional optical microscopy alone. Therefore, electron backscatter diffraction has become an important tool for understanding material behavior and geological process at the microscopic scale, according to Bois et al. 2025. Hi, me again. So, for this slide, let's go to talk about the mechanism of electron backscatter diffraction. So, firstly, the sample is placed inside the scanning electron microscope and exposed to electron beam. Next, the interaction between electron beam and crystal lattice produce backscattered electron that form Kikuchi patterns. Subsequently, the electron backscatter diffraction detector captures the patterns and transfer the information to a computer. Finally, the data are analyzed to determine crystal orientation, grain boundaries, and phase distribution. In this study, in situ electron backscatter diffraction was used to monitor microstructural changes during tensile deformation in real time, according to Bois et al. 2025. So that's all.
Today, I will present the real-world implementation of scanning electron microscope or SEM in geology and earth science. As my friend has stated just now, SEM is a powerful microscope that uses electrons to produce highly detailed image of materials at microscopic scales. It allows scientists to observe structures and composition that cannot be seen using ordinary microscope. Now, let's get right into it. The first application is mineral exploration and mining. Mining companies use SEM to examine rock and ore samples for valuable minerals such as gold, copper, and iron. The microscope can identify tiny material grains and determine their chemical composition in great detail. This helps mining companies locate profitable mineral deposits more efficiently while reducing unnecessary excavation waste. For example, gold particles that are too small to be seen using normal microscope can be detected inside rocks using SEM analysis. The next application is oil and gas exploration. Petroleum geologists use SEM to study pore spaces in rocks, shale formation, and rock permeability. These microscopic pores determine whether oil or natural gas can be stored underground. By analyzing these rock structures, companies can better identify oil and gas reserves and reduce exploration costs. For example, SEM imaging is heavily used in shale gas exploration to determine whether rock layers can trap natural gas. Another important application is fossil and ancient life studies. Paleontologists use SEM to study microfossils, fossil shells, and ancient microorganisms. According to research, the SEM-BSE technique improves the visualization of cellular structures in petrified fossil woods, including vessels, tracheids, and medullary rays. It can even reveal fossil ultrastructures at nanometric depths. This technology helps scientists determine the age of rocks and improve our understanding of evolution and Earth's ancient history. For example, SEM analysis of marine microfossils helps scientists study ancient ocean condition and climate change. And the final application is the environmental pollution analysis. Scientists use electron microscope to identify toxic particles, heavy metals, industrial pollutants, and microplastic in soil and water. The microscope helps determine the source and the composition of the contaminants in the environment. This technology helps monitor pollution levels and assist government environmental agency in environmental protection and cleanup efforts. For example, SEM is used to study airborne pollution, particles produced by factory and vehicle emissions. In conclusion, SEM plays an important role in geology and earth science because it allows scientists to analyze materials in extremely fine detail. Okay, thank you.
So for benefits, first of all is provide detailed image of mineral morphology and surface texture, which are essential for identifying minerals and understanding their growth patterns. Next, for the second one, is able to perform analysis at cryogenic temperatures and at variable humidity and variable pressure. So for the third one, is it is uniquely suited for examining beam-sensitive material as well as naturally geological and biological specimen. For the fourth one is it is highly applicable to environmental systems where capturing underlying microbial plant-soil interactions requires preserving specimens in their pristine, hydrated states. So for the last one is, with a simpler design and fewer moving parts, desktop SEMs don't need much maintenance. So this will keep downtime to a minimum, so you can count on consistent and reliable performance. So 4 challenges. First, destructive preparation, cutting and fracturing. Geological specimens, including rocks, minerals and fossils, rarely permit direct examination in their native state. Instead, they must undergo invasive preparation such as mechanical cutting, fracturing or polishing into thin sections and minute chips to accommodate the restrictive dimensions of the microscope's vacuum chamber. So second, vacuum chambers versus moisture. Moist geological sample or those containing clay minerals must be thoroughly dried and stabilized. Introducing moisture to a high vacuum chamber can cause outgassing, which disrupts the vacuum environment and can damage fragile clay structures. So third is infrastructure requirement. Conventional electron microscope are massive, sensitive and stationary laboratory equipments, so this creates a major delay between collecting samples in the field and analyzing them. Lastly, dimensional bias. SEM imaging and automated mineralogy software only analyze flat 2D surface because geological features like mineral, grains and fractures are actually 3D. This two-dimensional view can introduce bias and miss hidden details just under the polished surface.
Now, we will look into future developments and innovation in electron microscope. Now, we will look into 4D imaging. Traditional electron microscopy captures flat, static snapshots, which is a single surface or thin slice frozen in time. However, the recent developments have discovered that we could actually achieve 3D and also 4D imaging in our electron microscope. So, how did this happen? Recent advancement in electron microscopy instruments have led to a significant rise in data acquisition speeds due to the introduction of new detector technologies. This progress results in not just enhanced image size, but also more complex physical data representations. Contemporary instruments can gather several terabytes of data in one session, producing real-time videos as well as spatially and momentary resolved 4D datasets. 4D STEM maintains the comprehensive reciprocal space information required for in-depth structural parsing by capturing an entire two-dimensional diffraction pattern at each scanned pixel. Conventional STEM takes a flat 2D picture of a sample, but 4D STEM takes a 2 grid of photos where every single pixel contains another 2D photo inside it. This preserves all the rich data that used to be drawn away, allowing scientists to see exactly how materials are structured at an atomic level. If you see the picture in this slide, we can understand how the development have changed since the 1920s until 2020, which we have already achieved the 4D camera that allow us to capture 4D imaging from electron microscope. Now, let's move on to the second one, compressed EBST technology. So, compressive EBST tackles the issue of slow data acquisition by selectively sampling probe locations and reconstructing the partial dataset through an in-painting technique that employs a dictionary learning approach known as beta process factor analysis (BPFA). This BPFA enable much quicker data collection without requiring improvements in detector technology. By reducing the number of probe positions, the overall damage inflicted on beam-sensitive samples is minimized mainly due to a lower total electron fluence, the cumulative number of electrons striking the sample, and a shorter total acquisition time. What does it mean? It means that for a sensitive sample, by using the compressed EBSC technology, we could lessen the damage that we inflict on them. Hence, these compressive sensing methods enable labs to conduct quick, low-dose acquisition that are appropriate for delicate materials. Now, we move on to the third one, which is deep learning enhanced in SEM. So for the first thing, to produce a full resolution image of a single geological thin section would demand over 70 days, meaning that imaging all 200 sections would take nearly 95 years, which is impossible, or that we don't have that much time to actually wait with the current electron microscopic techniques. And in order to overcome this, researchers have used deep learning. So, deep learning addresses this issue by training neural networks to rebuild high-resolution detail from image captured at quicker, lower quality scanning speeds, thereby making rapid imaging geologically comparable to slow detailed imaging that would actually take years to actually solve and complete it. Hence, deep learning offers a groundbreaking solution featuring a new workflow that dramatically speeds up scanning electron imaging of Earth materials by incorporating integrated image registration and resolution improvement. So some of examples of deep learning that can be used to track the size and orientation of nanoparticles in 3D space, which is vital for fields like additive manufacturing and catalysis. Researchers have used the mass-R CNN model to automatically measure gas atomized nickel superalloy powders in SEM image. Automation AI in microscopy. So, firstly, let's talk about SEM EDS, which is Scanning Electron Microscopy SEM, which for high-resolution topographical imaging that was used side by side with energy dispersive spectroscopy EDS. So, the integration of SEM with EDS and image analysis software has been present in mining for many years, yet the current AI-driven evolution marks a major advancement. Instead of comparing spectra with a static library, contemporary systems utilize machine learning classifiers to deal with overlapping signatures, trace elements, and complex compositional variations among mineral species that previously needed expert analysis to be solved. At the image provided in this slide, we can see the flow of how it actually works between a human researcher and AI agent that's been integrated in the electron microscopy technology. So we can see that the human researchers still act as the leader in this situation, but they are working with a team of agent, which is not human, which is like software and AI and all others. And researchers created Distiller, a web-based platform that acts as a bridge between microscope detector and a supercomputer.
In conclusion, electron microscope can be used not only to analyze about geology and earth sciences, but also in many types of research in the industries, such as life sciences and medicine, nanotechnology, and also forensic sciences. Other than that, electron microscope gives a lot of benefit to the researchers to obtain a lot of useful information much more easily. This invention can be developed or improved into more powerful electron microscope than what we have now. Lastly, electron microscope is a tool that overcomes the limitations of optical microscope by using electron beams instead of light.
That's right.
Thank you.
Thank you. Bye.